it's my pleasure to introduce Sky. So Sky did his undergrad at Clarkson University in upstate New York in physics. Then he moved across the pond, did his PhD in applied math at University of Sheffield. Then he came back, did a postdoc in chemistry, so you can see kind of jumping around fields a little bit, at University of Massachusetts, Boston, where he was a research assistant professor before coming here to Northwestern, where he has stayed in chemistry and is now a research associate. So Sky combines techniques from statistical mechanics, information theory, and dynamical systems to understand far from equilibrium systems. Today, he's going to be telling us about techniques from quantum mechanics, in particular tensor networks, that can be used to understand classical reaction diffusion equations. And I'm very excited to hear about this because when I was in New York at the Flatiron Institute at the Center for Computational Quantum Mechanics, it was all tensor networks all the time. And I had no idea, I still have no idea what a tensor network is. So I'm hoping that by the end of the talk I will.
I think that's the goal here.
So take it away.
Thank you very much. So thank you so much for having me here and getting to speak to you about some of this recent work I've been doing with Todd Gingrich. And so today, what I want to talk to you about is kind of a classic problem in statistical mechanics. And we're going to talk about how do you connect microscopic kinetics with macroscopic observables. In particular, we're going to be we're trying to figure out what is the rate of transitioning between like metastable basins in a chemical reaction network. Now, I've been warned, this is a mixed audience, and so I'm not going to expect that you know anything about rare events, or most importantly, tensor networks, or even chemical reaction networks. So when we're in those sections, feel free to just kind of space out, daydream, whatever. And I'll wake you up when it gets interesting again. Okay, so let's see if we can get rid of mouse. Okay, so this work, I guess we can't, has recently come out. So if you want any of the gory details, you can find them there. Okay, so the way this talk is going to work is the first thing is I'm just going to give a super brief overview. So we're just going to crash through the main ideas here because there's a bunch of pieces we're going to put together. And then once we put those pieces together, we're going to go back and we're going to look at them in more detail. So the class of problems we're going to be studying today is we're going to be looking at discrete state continuous time Markov processes. So what we can think of in the simplest case is we can imagine when we say that we're going to have some lattice of sites, okay? And now each of these sites, we're going to have some particles or balls or whatever you want to think about them. And we're going to assume that these particles can hop, right? So there's going to be some rate, some stochastic diffusion coefficient for allowing them to hop from site to site. And if we fix a finite number of lattice sites and we fix a finite number of molecules, there's actually already interesting problems that we can ask about this super simple system. So for example, we could put all the particles on one side and we could ask, what is the average time to cross the lattice? But we want to make things more complicated. And so the next step is we can not have particle conservation. We can allow the creation and the annihilation of particles. So for example, we could have some rate C that we're going to add particles to our system. And now the problem by making this innocuous little addition is that the number of states or configurations of this system is going to immediately become exponentially large. So let me explain what I mean by this. If we imagine that at each lattice site, we can have a certain maximum number, maximum occupancy. So for example, we could have 1, 2, 3, 50, 100 molecules per site. So we're going to make this cap M. And we're going to imagine that it's 85 just because that's the number we're going to use the rest of the simulations or the rest of the calculations later. And so there's a space of all possible configurations, right? Omega to the L, where L is the number of lattice sites of our system. And so very quickly, as we grow the number of lattice sites, the number of configurations of the system is going to become astronomically big. So 10 to the 15, 10 to the 20 configurations. I don't really have a sense for that. So we're going to come up with this silly unit. We're going to call it a galactic unit, right? So Hubble has estimated that there's 2 trillion galaxies in the visible universe. And so this is going to be kind of our unit of reference, right? So we're gonna say that if we're around 6 sites, for example, 6.3, then that's equivalent to 1 galactic unit. So the number of configurations will be the same as the number of galaxies in the universe. The largest simulation, the largest calculation we're going to do here for our full reaction diffusion system is going to be 86 to the 8 configurations. So 1,500 times the number of configurations in the visible universe. Now, if I have this large a space, how am I going to calculate things in here? There's 2 main approaches, right? The first approach is we can do what's called kinetic Monte Carlo methods. So we're simply just going to sample stochastic realizations of whatever the rules of our system are. So the observable we care about here is the number of molecules or the occupation of each lattice site. And we're going to ask, how does this change in time? And because we're tracking each individual molecule of our system, this is going to change in discrete numbers. We're going to take discrete hops. But there's a completely different way to look at this system. So these systems we could also simulate at the ensemble level. So the dynamics here is going to be called the chemical master equation, and we'll explain what that means. But the idea is that instead of looking at an individual realization of my system, I'm going to look at the probability of each individual configuration in time. So the thing you want to understand is this joint probability. Now, if I have 15 galactic units of configurations, this distribution is going to be extremely big, right? That is a huge list of numbers I need to know. And if I want to know these in time, then I need to know all these numbers at each moment in time. It would seem like this is a complete fool's errand. And that's why most people stick with this approach. But what we're going to do today is we're going to show that actually, if you combine some known methods, you can deal with systems more complicated than this, full reaction diffusion systems at the stochastic level by looking at ensemble evolutions. Okay, so how are we going to do this? Well, what we're going to do is we're going to think of this thing not as a list of numbers, but we're going to think of it as a big box of numbers, a rank L tensor. And so we're going to use a lot of these cartoon diagrams here. So basically this big rectangle, it's just going to be some box of numbers, and we're going to feed into it the occupation of each lattice site. So how many molecules are in each lattice site? And that's going to output a number, a probability. And the approach here is that because this thing is just as big as our distribution, it is our distribution, what we're going to do is we're going to encode it. And we're going to use what's called a tensor network to encode it. So instead of looking at this giant box of numbers at once, we're going to look at these low-ranked tensors. So I'll explain what these are, but you can think of each of these as smaller boxes of numbers, right? This thing, because it has these 2 legs sticking out, this would be a matrix, a rank 2 tensor. This would be a rank 3 tensor. And the idea is that these together are going to be much smaller than this one. And yet, if I feed in the occupation, I still get my probability back. Ooh. Now, what's more is we can use this to find evolutions of this distribution. So for example, our distribution here, P, that we can't calculate, we can think of it as living on this manifold where every point is a possible joint distribution. And we have no idea the rules for how to evolve it in time because we can't solve this directly, it's too big. But we also have another manifold, which is the manifold of all what's called matrix product states, which is what this tensor network is. And so what it turns out is that because of the structure and the properties of this tensor network, not only is it a more efficient representation, we don't have to evolve this whole thing in time. We get to evolve one site of this tensor, say from some time t to t prime, and then we can sweep through and evolve all our tensors individually. So we trade solving one large time evolution problem for a sequence of smaller time evolution problems. And then at the end, this new matrix product state is equivalent to the joint distribution at some time t prime. Okay, so that was like crash course, like an overview of everything. And now we're going to step through and look at these pieces in detail and show how we're actually going to put this together. Okay, so the easiest way, I think, because there's a lot of pieces, we're going to look at one example. So here we're going to look at what's called a Schlogel example, the global model. And this is like a quintessential model of what's called bistability. And we'll see what we mean by that. But now at the beginning, instead of having a bunch of lattice sites, we can think of like just these amorphous platforms for molecules. We can think of each one of these as going to be like a reaction voxel. So this is the chemistry, if you will. We're going to have a box, and in that box, we have a bunch of molecules bouncing around. And we're going to make the assumption right now that there is an equal probability of finding the molecules anywhere in our reaction voxel. They may not be probable at any one place, but they'll be equally probable throughout. And so that's our well-mixed regime. And so the rules for how these molecules are going to change is given by the reactions, the elementary reactions of our system. So the first one here, we're going to have, for example, 2x molecules plus an A molecule can, with some rate C, turn into 3x molecules. So all the pieces of this are what we're going to call our chemical reaction network. So in this case, we simply have 3 species. This is a very simple one. We have X, A, and B. And now we're going to subdivide that into the species that are changing in time, the dynamic ones. In this case, it's just X, and our chemostatic species. So we're going to imagine that we have some reservoirs attached to this reaction voxel that feed A and B molecules into our system. So anytime an A molecule gets used up in this reaction, another one will be given by the reservoir into the system. So the number of A and B are going to be constant in time, and X is going to be changing. Each reaction is going to involve a finite number of molecules changing. So we also have these stochastic coefficients that simply tell us how many X's change in each reaction. And we have our rate coefficients. So these are going to be our stochastic rate coefficients. So this is the model that we're going to consider. And why do we consider this bistable? Well, if we look at it in the right parameter regime, and we look at one stochastic realization of this reaction, what we see is that the system is going to bounce around in some high molecule number region, and then it's going to stochastically switch, and it's going to bounce around in some low molecule region. And we see this all across reaction networks in nature. And so
what do you mean by correct parameter regime? So like what's the conditions on the C's that gives?
Yeah, that's very good. So it's actually conditions on the C's combines with the A's. So there's 3 different regions the system can be in. You can have 2 stable. So when we talk about this bistable region, we're talking about in the large molecule number limit. And so there you have fixed points. And so in the certain parameter regime, we're going to have 2 stable fixed points and 1 unstable. As we adjust our rates or in our A and B, we're going to shift into a new region where we only have 1 stable fixed point. And so then you would only convert, you would simply converge to 1, you would only see oscillating around 1 value. So great question. Yeah.
So the stochasticity here, that's just due to the finite size effects. If it, as n goes to infinity, it goes to 1 of the fixed points.
Exactly.
Stays.
Yeah.
Okay.
So in another version of this talk I've given, I emphasize this point that every pattern that we care about here, you have to simulate it in the right size regime, right? So you can look at famous examples like the brusselator, where you can approach a limit cycle. If I simulate that in the stochastic regime, the limit cycle behavior completely disappears, even though all my rates are exactly the same. The only difference is that my volume is not large enough. So yeah. So here, when I say stochastic, I mean this finite number of molecules. So in this, for example, here, we're around like no more than 80 something. Okay. So we're going to bounce back and forth between the system. And right now, this is just well mixed, right? It's a 1D random walk. The number of X molecules can go down to 0, or it can grow up to whatever level it wants to. So we're going to be a little more precise. We're going to think of this region up here as like a metastable basin, right? We're going to call this one A. And we have a new metastable basin down here. And the question we really want to answer about the system is, what is the rate of transitioning between A and B? Okay, while this is a 1D problem here, everything is going to be super easy. So how would we actually calculate this thing? We're simply going to ask, we're going to run a whole bunch of trajectories, or one trajectory that's really long, and we're going to ask the time it takes to see the transition from A to B, given that we started in A. And then the rate of transition is simply going to be 1 over the average time to flip. And so if we look at lots of flips, we're going to see that this is going to converge to some number, A, B. And this is what we're going to call our rate. Okay, so we're done, right? We calculated our rate. We can all go home. Well, not quite, because this is just a toy problem. We can make this problem a lot harder. And how are we gonna make this harder? Now we're gonna add diffusion to our system. So instead of having one reaction voxel where our reactions, any of our reactions can take place, we're now gonna string them together in so like a 1D lattice of reaction voxels of some length L. And we're gonna allow that our particles are gonna diffuse between our reaction voxels. And so together, this is gonna form what's called a reaction diffusion master equation. And so now you can see the problem already. The number of configurations of this thing is going to grow really, really large. So what is the configuration of this? Instead of just the number of molecules, we're back to the place where we have to ask what is the occupancy of each voxel. Our basins are no longer just are you larger or less than some number. So now A is going to be the set of states where the occupancy of a voxel is greater than some value lambda alpha for all, or sorry, lambda A for all L. So this is going to form like some hypercube. And then likewise, B is going to be the set of states such that all voxel, the occupancy of all voxels are less than some value lambda B. Okay, so these are now regions, like high dimensional regions of our configuration space. And we want to ask, how do we transition between these regions? We're going to set our cap to 85 molecules. The kinetic sample Monte Carlo doesn't care about the cap. The cap is just there because when we build this into operators, we can't have an infinite operator on our computer, so we're going to have our cap. Basically, you just set this to whatever is convenient to your system. And so this gives us n+1 for the L configurations. So we have n molecules per voxel site. We have the vacuum state, which is no molecules, and we're going to have L voxels. So if we start trajectories in one of these, in some region A, we're going to sample them from the stationary distribution of being at A, and we're going to run these trajectories until they first get to B. And if we average all of these, sure enough, we can calculate the rate of going from A to B. And there are some error bars on here that you can't really see in the log linear plot. But the point is that as we increase L, the rate of transitioning is going to become exponentially rare. So how big are these systems? Well, if we're at L is equal to 6, this is only like 0.2 GU as we call it. But as we go to 17, one step up, we're already at like 34 trillion configurations in our system that we may sample, or 17 GU. So you can ask, is there like a cost for trying to sample directly these large systems? And the cost is that the time it takes to do these calculations is really unfortunate. So the number of CPU hours to calculate these rates directly using Gillespie looks like it's growing exponentially. And if we put this on a log linear scale, it actually looks like it's growing slightly super exponential. Now, I just want to say that I'm not against Gillespie here, right? I think Gillespie is one of the most beautiful algorithms in the world. The nice thing about Gillespie is it's super general. What did we input to do this calculation? Simply the number, we just have our rules for our reactions, right? We don't need to know anything else about the structure of the configuration space or the state space. And yet we can still do these calculations. But at L is equal to 7, it took 13,000 hours to calculate this rate from A to B. So that's unpleasant. If we can ask what would happen if we wanted to go one bigger, and now we're at approximately 11.9 years to do this using Gillespie, clearly we need another solution, right? This is not going to work. Yes.
But is this problem parallelizable?
So this is the total number of CPU hours in parallel. So the point is that, like, so you say, I have a bigger computer. Okay, well then I say you can go one more. And you say, well, I have a bigger computer. Well, you got one more. Like, if that, like, it's just bad. So what people do normally is they build these like advanced sampling techniques, like forward flux sampling, which if you're interested in, we also can talk about later. And what these do is they trade additional information about your reaction network to get around this exponential growth. So by knowing more about your system, you can turn this exponential cost into a sub-exponential cost. But the price for that is that you need to know intimate knowledge, such as how does the system transition from A to B? But if I already basically know how it transitions from A to B, my rate I get for free. So Okay, so just to recap, our kinetic Monte Carlo, we're going to count individual reactions. We're going to build ensemble statistics. This will give us our rates. Our challenges are that we don't, how many trajectories do you need? This exponential cost comes mainly from two places. One is that as you increase the number of molecules in your system, the time between reactions is going to exponentially go to zero. So you end up sampling needing to generate an exponential number of random variables to decide when all your reactions occur. The other problem is that really this only measures what is in the bulk of the distribution. If I have a rare event I care about, I need to simulate and wait for that rare event to occur. If it's exponentially rare, then I have to simulate for an exponential amount of time. So we would like to get around these two problems. Okay, so here's like the plan for how we're going to get around these problems. The first is we're going to look at our ensemble evolutions in a little more detail. And then we're going to introduce a second quantization, which will basically be an encoding of our chemical reaction network into a second quantized form. This second quantized form is not merely window dressing. What it's going to do is it's going to allow us to take our set of reactions and convert them into a tensor network. And then with this tensor network, we're going to be able to calculate our rates directly from the ensemble evolution. Okay, this is mean for me, so I don't forget. We're just in the well mixed. We're going back to the well mixed right now, and we'll add diffusion again. So the goal is to know how the probability of each configuration changes in time. Our equation of motion is given by this right here, which is called the chemical master equation. And it simply says that the change in probability of any configuration gets a contribution from a sum over each reaction R. Each term has two pieces. One of them, for the change in probability of being an N, is this first term, which is all the different ways I can transition to that configuration for my reactions. The other one right here accounts for already being at some instantaneous time t in that configuration. Each term has two terms. One is our joint probability, which we've already talked about. And the other is our what's called our propensity here. So this is the probability per unit time that a reaction will happen in some infinitesimal moment dt. Okay, so this gain-loss equation is our dynamics, but there's another way we can think about this thing. Instead of looking at making a list of each configuration and asking the change in probability, if we're in the well-mixed regime, we can write down this in a matrix form. So for each set of reactions, we can figure out what the transition matrix it's called that represents those reactions. So for example, our B goes to X and back. Here is the transition matrix. The off diagonals simply give us the transition rate of that transitioning between configurations due to that reaction. The diagonal is there to conserve probability. And likewise, if we have our 2x plus a goes to 3x, that a chemostatic species gives us another reaction. And because we're in the well-mixed regime, this is all easy. So the linearity says we can add these together to give us our total dynamics or our total reaction. Because this is a small system, we can simply form the propagator by taking the matrix exponential. We can evolve this in time. And if we're interested in our stationary distribution, which we will be, and we often are, then we can evolve this in principle, we can evolve this dynamics until we converge to whatever the stationary distribution is. The problem, all right, so the change here in viewpoint is now we're evolving all possible trajectories, right? The nice thing is we don't have a sampling error from this in a sense, because this is all trajectories are in this dynamics. As we'll see in a second, we can extract rates directly from this, and our parent vector, as we said, gives us our distribution. Our challenges are twofold. One is merely like minor, is that we want to organize the space once we go to reaction diffusion systems. But the main problem is that this state space is, of course, going to grow exponentially. Okay, so how does one extract a rate when you don't sample your system? The way you do it is you simply take your distribution and you're going to project it, your stationary distribution, in our case, into our basin A. And then we're going to renormalize this. So by renormalizing, we're going to project onto that distribution. And then this bra of ones is going to add up all that probability. And I think this will play. And then we can, as we evolve our dynamics, our probability, of course, is going to flow into B. And what are we going to do as this probability is flowing into B is we're simply going to project onto our B region with our a different projector. And we're going to ask how much probability has flown into B. And then we're going to add up all the probability from all the configurations that are in region B. So what does this look like if we plot this? What are we actually doing with this? Is we're asking what is the conditional probability of starting in region A and getting to region B in some time t. Now, if our basins are deep enough, we're going to get a picture that looks like this. So initially, no probability can reach B, right? But there's some time scale called molecular time scale where we transition, where the weight has reached B or the trajectories have reached B, and now we grow into this linear regime. The rate that we found before now is simply just the slope of this line. The third region, which is nice that we don't need to care about, is the relaxation time for the probability in B to reach its stationary value again. Typically, we only need to simulate until we reach this molecular time scale. So we only in a little region beyond it, right? This whole form of the evolution, which is the really expensive part, or more expensive, we're not going to need to worry about that. So the advantage of looking at the ensemble level is basically we don't have sampling errors. And in theory, we only have to simulate for a small amount of the total relaxation time of our system. But again, this only works for small systems. Okay, so how are we going to go and make this jump from our well-mixed to our reaction diffusion system? The first two steps, what I already mentioned, is now we're going to encode this in a second quantized form. So this is called the Doi-Politi formalism. And what this is going to allow us to do is it's going to allow us to give a seamless way to go from our input, the CME dynamics, to our tensor network. So the first thing we do is we're going to define a basis for our second quantized encoding to live in. So we're going to define what's called the Fock basis or the occupation basis. So each of these set of basis vectors, there's a basis vector that tells you the occupancy of each voxel. So here, our cartoon, you can think of these blue as X, like A is red and B is black, but don't try and calculate the concentration because I wasn't that careful. But this is going to tell us how many, there'll be a basis vector for each number of X molecules in each voxel. If we form the tensor product space, this gives us a new set of vectors, which will account for all the possible configurations of our system. This distribution, we can then write the representation of this distribution of our original joint distribution in this set of basis vectors. And this gives us something that looks like a wave function, if you will, but this is just like our ket state. It's our ket representation of our joint probability distribution. Okay, the next part is that we need to figure out some way of taking our reactions and converting them into our effective Hamiltonians. So we're going to call these effective Hamiltonians because there's no energy here like normal Hamiltonian. This is just the number of molecules. So to do this, what we need to do is it's going to look just like quantum mechanics. So this is where things start looking quantum, is we're going to define a set of creation annihilation operators. X will be our annihilation operator, X dagger will be our creation, and we're going to say that these satisfy this commutator relationship. We're also going to have this positive semi-definite number operator here. And together, these are going to allow us to move around our Fock space. So if I have X and it acts on some Fock vector, what's it going to do? It's going to give me a number out front, which will be the number of molecules this vector accounts for. And then it'll move me to the minus one down one Fock vector. But now notice what happens when I act on X dagger. I don't get a number out front anymore. Well, I do, it's a 1, but I move to the X plus 1. So this is the difference between, one of the differences between this Doi-Politi representation and the normal like quantum harmonic oscillator is these are not going to be conjugate transposes of each other like you have in the quantum case. Okay, if we put a cap on these, then these just turn into matrices, and we can see the X dagger lives on the first lower diagonal, X lives on the first has its counting numbers on the first upper diagonal. Okay, so in order to go from the input, so the change of one microstate to this new encoding, basically it's a turn the crank method. Now, I'm not going to go into all the details of how you do this, but basically you take your chemical master equation for each reaction, and you're going to look at the structure of this propensity. And then you're going to substitute in the corresponding creation annihilation operators that are going to reproduce this dynamics. And then what you get is you get these equations that intuitively they kind of make sense, right? This first reaction, I'm going to annihilate 2x and I'm going to create 3x. If I look at my equation over here, I'm going to annihilate, I have 2x squared, so I'm going to annihilate 2x, and I have x dagger cubed. I'm going to create 3x. The second term here is going to account for our diagonal and conserve our probability. These projection operators you may notice in some of these terms, these just come from having this finite cap. If I allowed an infinite number of molecules in my system, then I would have the normal like second quantized form and I wouldn't need these projection operators. Okay, so the idea is that you give me a set of reactions, I convert these into a set of effective Hamiltonians. Due to the linear structure of my chemical master equation, I can write like a super operator that tells me it's the effective Hamiltonian for the whole reaction just by summing these for each voxel. And likewise, I can introduce diffusion into this equation. So now we can go back to our reaction diffusion problem. So diffusion is going to be a first order reaction where the diffusive hopping from sites L to K is simply going to be our stochastic rate, our stochastic diffusion coefficient. And then we're going to have an extra molecule. We're going to start with an extra molecule at site L, and we're going to end up with, and we have one less molecule at site K. And so you can kind of see this hopping mechanism in here. And then you convert this into this creation, these effective Hamiltonians where we have our right diffusion. So we can lose one at site L and create one at L plus one. And likewise, we can lose one at L plus one and create one at L. Oh, and the stochastic diffusion coefficient is just related to your normal diffusion coefficient that you know and love divided by the length of your reaction voxel. Okay, likewise, we can add all of these together and we get our diffusion operator. Perfect. So to recap, our Doi-Politi converts our local CME into this global coupled equations here. Now we're finally going to deal with this many-bodied problem, right? So this is the thing we've been building up to, is how do you take this thing right here, right? This vector is going to be like 10 to the 15 states long, and this matrix would then be 10 to the 15 by 10 to the 15. I don't care how sparse your matrix is, you're not going to be able to write that thing down. So how are we going to deal with this? Well, we're going to go back and we're going to think of this, remember this distribution as not as a point, but as a rank L tensor, where if I feed in all these numbers, I'm going to get out a probability. And we're going to go back to this cartoon. So these legs that stick out, these are going to be what are called our physical indices. So they simply tell us, they account for all the possible numbers of molecules we can read into each site. So this thing is going to be our rank L tensor that's going to represent our joint distribution over here. And the whole problem is, can you take this exponentially large tensor and encode it into something that is not exponentially large? So how do you do that? There's multiple ways to do that. The way you do it in practice is you're going to perform a sequence of singular value decompositions. So instead of thinking this as a giant vector, right, we can rearrange the indices however we want. We can write our original tensor as a matrix where n1 is going to be our rows and everything else is going to be our columns. By writing it this way, they call it unfolding in the mathematical literature, we can then take an SVD decomposition that gives us a new matrix, U, a diagonal matrix S, and then everything else is just we're going to call V. Okay, so here I'm going to have I've introduced these horizontal lines in my tensor network descriptions. So I have our physical index, and these lines are basically what's called our bond indices. And what they're doing is there's these fictitious degrees of freedom we've kind of introduced, which are going to account for the correlation between this tensor and everything else in our system. And so they're encoded basically in the singular values, so the positive numbers that lie on the diagonal of this matrix S. I've not written all these indices in the sums here, so this is just in matrix multiplication because it gets very ugly. Okay, but the next step is we're going to take those singular values and we're going to absorb them into here, and this gives us a new matrix C. And we can then rearrange this one in the same way, and then we can decompose C. And now look what we have. We have two low rank tensors. This one has 3 legs, so it's a rank 3 tensor, and one rank 2 tensor. And we can continue this process, and lo and behold, we end up with a matrix product state, which is an example of a tensor network. Now, have we actually finished the problem? We haven't quite, because if you look at how big all of these indices are, they're going to grow exponentially up to the rank of your tensor over 2. And so you have an exponential, if you think of these as like the parameters of an approximation function, then you've introduced an exponential number of parameters to approximate your exponentially large tensor. So there must be some path forward. And the path forward is simply to go back and look at your singular values. So remember, each of these numbers is a positive number that tells me how important a set of basis vectors are at representing my original high rank tensor. It just so happens that often we get lucky and these singular values are not all equally important. If you plot the diagonal numbers on this matrix, the singular values often decrease extremely fast. And so what this means is that we can say we're going to accept a certain amount of error in our approximation. So we can set some value, call it kappa. This is going to be our bond dimension of our tensor. And then what's going to happen is we're going to say we're going to throw away all singular values that are smaller than whatever this value is at kappa. And the product of this is that now we have a new matrix product state that does not grow exponentially in our bond dimension, but is finite. Yes.
So you're interested in rare events.
Yes.
So how do you know that the rare event doesn't lie out beyond where you're cutting things off?
That is a really good question. And to be honest, when we first started doing this, we had no idea if they would work. But the truth is that you can't think of this as like, this is the tails of my distribution, and this is the average of my distribution.
This is state space, I understand.
All right.
Yeah.
So it's like, we're like adding levels of detail to the approximation of the entire, whatever this high dimensional thing is. And the answer is that it turns out you don't need to keep them all. And more precise answer, I don't know. Like it was not a given when we started doing this that we would be able to do this. Yeah.
Is the effective rank or the cutoff that you can use on the SVD related to like the connectivity in state space?
Yes, it is totally. So we're using a matrix product state right here, right? But there is an entire zoo of tensor networks. You can build Mira, you can build tree tensor networks, which this is technically a trivial one. You can build tensor networks with loops, and all of these have different singular values that represent the connections in that tensor, and they encode correlation differently. This is not the right tensor to use for all different systems. What the right tensor network is to use for a given system is also like a question one has to answer when trying to use these methods. When this happens, that your singular values become extremely small, you're satisfying what's called an area law, which simply means that if I have an original network, and I imagine I'm going to look at some subspace of that network, and I'm going to ask how does the correlation as I grow for an arbitrary subset, as I grow the size of that network, it's going to be upper bounded by some number. And so when that happens, then you end up having this collapse in your singular values, and then you basically get like extremely accurate representations of your original high rank tensor with very small bond dimension. And you can quantify this. So back in 2006, it was shown that if you give me any matrix product state, or basically any rank L tensor like this, and I give some matrix product state approximation, the L2 norm between those will never be worse than this function over here, which is basically a sum over the amount of truncation I'm doing at each bond index of this error function. And this error function is simply the sum of the singular values I'm throwing away squared. So like, as I throw away fewer and fewer singular values, this thing goes to 0 and I approximate my original tensor. So it's like a controllable error that we're introducing to get rid of this exponentially large space. And so you see now, yeah, I've changed. Now this is not P sub t, right? Now we're going to call this Q sub t because this is like our approximation function for our original high rank tensor. Any other questions? These are great, by the way. All right. So you can also do this with your dynamics. And so now instead of forming a matrix product state, we're going to form what's called a matrix product operator. And what happens is by writing this in our Doi-Politi form, it looks horrible, but it's actually relatively easy to form a matrix product operator out of this. In most cases, you can actually analytically just work out what the matrix product operator form is for a given set of reactions. So for example, for the Schlogel model, we've written down what the exact MPO is for that set of reactions. But if you don't want to do that, or you can't, there's actually also just automated software now that if you can write it from the quantum world, because we're stealing all their good ideas, if you can write down your set of reactions in the second quantized form, there's automated software that will give you a matrix product representation of that reaction. So once we have our set of our matrix product operator, so just so you can read what this is, right? We have two sets of physical indices now and a bond indices connecting them. So like you can imagine, like I'm going to read in a set of numbers on one side, that's like my initial configuration, and then I'm going to get out a configuration on the other side. And so this whole thing tells me what is the transition rate of going from some total configuration M to some total configuration N. Okay, so what we've done is we've taken our original coupled set of equations that we can't solve, and we've come up with a new set of like approximation functions with a controllable error. So this is our new equations that we want to solve in time. But there's a slight problem. So there's actually lots of ways to evolve this type of system, I should say. There's like all these acronyms, TEBD, time evolving block decimations, Krylov methods. We're going to use something called time-dependent variational principle. And we're going to use that for two reasons. One, it conserves probability. For the version we're using, it should guarantee conserved probability. And two, it's extremely general. So what's going to happen is we're going to imagine that our dynamics is going to live on this manifold of all possible matrix product states. And the problem is that if we try and build this propagator directly, what's going to happen is in general, we're going to leave our manifold of matrix product states. And remember, that's what gave us our controllable error, that we lived on this space of all approximation functions that have this tensor network ensembles. And so what TDVP does is it says, let's not directly solve this thing. What we're going to do is we're going to build a projector that's going to say, okay, I've left my manifold, but I'm going to project down to the variationally closest place on my matrix product state manifold. And actually, it's not quite the matrix product state manifold, because the projector acts exactly here. We're actually at the tangent space of the matrix product state manifold, but the outcome is the same, is that our MPS, if we evolve it in time, it will never leave that manifold. The projector is a sum of these terms, which in themselves are horribly complicated things. But basically, all you need to know is that this first one, which we're calling P plus, each one of these is going to act on one core tensor of our MPS. And then each one of these P minus accounts for interacting with one of our sets of our bond indices. And what happens is, due to the structure of this thing, the projector, we can think of it as acting on each one of these at a time. So instead of having to evolve this matrix product state in one go, like building the propagator for the whole MPS, as I mentioned earlier, we're going to build the propagator, we're going to trade that for like a term that's going to evolve locally. So we're going to have a local problem we're going to have to solve. For example, this one would be like acting with P1 plus on H. And so now we have this local term that we can evolve forward in time using our local matrix exponential. And that evolves this one in time. P minus term, we then have to evolve, which accounts for evolving this bond dimension actually back in time. And then we can evolve we can apply the next projector, and then we can solve the next local problem. We evolve the next one forward in time, and we can sweep through. And so almost miraculously, we get to evolve all these local problems, and it's equivalent to evolving the entire matrix product state forward in time. And now, because we've evolved in time, we can ask for the probability of any configuration. Okay, so let's look at this thing, some pictures of this. So imagine we have our high dimensional space here, and we can ask, I can't visualize the distribution here, but of course I can ask for like a marginalization or a slice of this thing. And so here, what we're picturing is the joint probability of evolving any point between voxel 2 and voxel 3. We've projected into our region A. And so here is our initial stationary distribution renormalizing to A. And what's cool is that as we evolve this thing in time, we can literally visualize all the different regions of our evolution. So one thing to note is I've numerically just set the A region to 0 visually, so because this flux of probability is very small. And it's hard to see it when you have to rescale everything. But initially we can see that the probability is just leaked out of A, so we're in this region. If we evolve for some time T, then we can see that our probability is just reaching our region B, so we're at our molecular time scale. And then if we keep going, we're going to flow probability from A to B. And we're going to build this conditional probability in time. Okay, do we calculate rates? Yes, we do. So if we set our bond dimension to different values, so here we've used a bond dimension of 20 and a bond dimension of 30. Remember, this is an extremely harsh approximation, right? If we're at 8 voxels, then this thing, our bond dimension should be like 86 to the 4 at the maximum. That is a huge number, and yet we've truncated it 30. So we basically get a lot for not much input here. But if we set kappa equal to 20, we can calculate the rate up to L is equal to 6. And then as we'll see in a second, our bond dimension is no longer large enough to like accurately model these high dimensional distributions. And so we need to go up to a bond dimension of 30. And then we can push beyond where we're able to do with our direct Gillespie sampling.
So what goes wrong if you keep it at 20? Well, how do you know?
This is what goes wrong.
Okay.
What goes wrong is that if you start to look at these probability distributions in time, you can see that they become extremely numerically unstable. So here is an example. This was just a small system, but it's the same for any system you look at. If I have a bond dimension of 5, you can see I get all these crazy, totally unphysical probabilities in time. And as I increase my bond dimension, I'm going to start converging to one smooth curve. In our case, we also have conservation of probability, which is a nice tool. If we start violating conservation of probability, our MPS is no longer representing our physical system. So we obviously know that we need to adjust something. And often the bond dimension is the go-to here. Okay, how does it scale? Well, here we can plot our CPU time from before, and we see that we get a really nice savings from this. If we look on a log scale, it becomes easier. So we can see that while it is more expensive, there is more overhead for small systems. As you go up in number of voxels or the complexity of your system, we get this turnover and things are starting to look much nicer. This is no big deal because we could just evolve this exactly down here. There's no point in using any of these methods. So what are some numbers? So this one took 13,000 hours. This one took 1,800 hours. This is not parallelized, by the way. So this is just in serial. At L is equal to 8, this took 3,200 hours. And this would have taken, as we know, 11.9 years approximately. So it's much nicer scaling. Okay, so just to conclude, we've built a largely mechanism agnostic framework. So like if you give me a set of chemical reactions network, in theory, I can encode these into a Doi-Politi formalism, and then I can write them as a tensor network. Whether it's the right tensor network is another question. We've shown that we can calculate rates for these reaction diffusion systems efficiently over multiple orders of magnitude. So that we did over 5 orders of magnitude in that example. And our cost is growing sub-exponentially to do this. We can apply this to arbitrary sets of state space, right? I defined what my regions A and B were. There's a natural subset of state space, but you don't need a certain number of basins like in some other rare event methods. You can specify whatever area of phase space you want. And we don't require any detailed information about the structure of our state space. So like we don't need to know what the reaction coordinate is to get from A to B in order to calculate the rate. You can just do it directly. Future work, I mean, there's lots of places to go. I've become really interested in gene regulatory networks. I think this is a great place to try and apply these methods. Anytime you have discrete space lattice models, stochastic lattice models, basically you should be able to apply something like this. As was mentioned, a really good question earlier about, is this the right tensor network representation? It's definitely, for this system, it works really, really well. But I can imagine I could have some network with lots of different chemical species. And now these species may be very correlated with each other in that they partake in the same set of reactions. But if I try and encode this into a matrix product state, they may end up very far away in my matrix product state. And so what that's going to do is it means I'm gonna have to pass correlation way down. And so the amount, my bond dimension, I'm not gonna get such generous truncation as I did here, because I need to have enough bond dimension to pass that correlation all the way down. So how do you deal with those types of systems is actually the problem we're really working on right now. And also, if you have other examples, I'm always up for other interesting ideas. So this is a bit out of date, but I'd like to thank Nils Strand here, who's now just started a postdoc at U Chicago, and Adrian here, who's at Sorbonne, who's a former postdoc. They're the ones that got me interested in tensor networks. I had no idea what they were when I got here, and now I think they're great. And obviously Todd for keeping everything running and everyone employed. So thank you very much.
So maybe some of the gene regulatory network applications, some of the environments cellularly are very crowded, right? And people are thinking about how do you simulate diffusive processes and kind of realistic, very complex geometries, right? Have you thought about this at all and perhaps how to adapt or?
So I know, well, that I think is a really hard problem for people working on it. I'm thinking more in baby steps here, right? Yeah, you can introduce diffusion and you can have some simple heterogeneous distribution of molecules and they can diffuse around. That's totally doable with here. I think if you want to push to these really large, realistic models, and like what you were talking about, then you're going to need to solve first this other problem that we talked about, is how do you efficiently encode that correlation from that dynamics into a tensor network. Then once you have that, yeah, then you could probably, then it doesn't matter what your geometry looks like. You adapt your tensor network to the geometry. Elson.
Hi, how general can these tensor networks be? I imagine that you can define them on an arbitrary graph. But can you still get meaningful calculation out of it if the graph is dense, has a lot of short loops?
If it's dense, yes. Like chains, I think, are very doable with this. But when you start adding loops, that's the exact problem that we were just talking about, is that your matrix product state now may end up having nodes on your loop that are far away in your matrix product state. So this is exactly what Todd and I are working on right now, are what are methods for generalizing these tensor networks to classical problems. In quantum mechanics, the structure of their quantum lattice models means that they often don't have these loops, or certainly when this stuff was, the problems they were thinking about when they were inventing these methods weren't loopy like we have in our classical reaction networks. So yes, you can always write down the tensor network. Whether you satisfy like an area law so that you can do this aggressive truncation, that's another method. That's another question.
And just as a follow-up, how much of this is relying on the particular properties of the Fock space you are dealing with? I assume that you have a discrete set of states, infinitely many.
So in theory, you can have infinitely many. The system here sets a natural scale that we cut off.
Yeah. In principle, that's not an issue, right?
No, you choose your cap for whatever your system.
And in the classical case, when it would be continuous, would that be an issue?
So there's an entire separate branch of tensor networks where people write down what look like continuous field theories and then map them into tensor networks.
Got it.
But that area is much less developed. Like this is like, we're using tools that are like between 20 and 5 years old. Those continuous tensor network spaces is, I think, I don't know, in the last 6 years really has been, people have really been attacking it in earnest.
Kind of the basic question about the rare event, kind of the whole purpose of this calculation. I get that. So if I understood correctly, you're starting it from initial state where it's all state A. You're looking at the transition rate to state B, and that's the rare event rate that you're finding. But is there a reason to expect that transition rate to be the same as the transition rate at equilibrium?
When you say the rate at equilibrium, what do you mean? So there's
You have some A and some B.
so the relaxation.
Yeah.
No, it's a totally different rate.
Okay, so can you get that second rate as well, or is that?
I imagine you could. So there's no reason why you had to a priori start in A, right? I could also run the same calculation if I wanted to start in B. And then if I have both rates, I think I can calculate this total relaxation rate.
Unless the rates are dependent on that distribution, then you'd have to know the initial equilibrium distribution, like. To
Well, we
me,
do know the stationary, we're sampling, our A is the stationary distribution.
okay, all right, because. I mean, it's not all A, it's a mixture of A and B as the stationary distribution, right? Or am I
Well,
misunderstanding?
in our case, because we're only looking, we only want the one directionality, right? In that case, we're just starting from projected into A. You could start in a mixture of A and B. You can start in any distribution you want. Like nothing here cares where you start. So I think you could calculate that rate, but I haven't tried to do it.
So you had a truncation M.
Yeah.
Which you picked to be 85.
Right.
So if how does that algorithm scale as you change M?
That's a great question. I don't know. It depends on your system. Like it can scale really badly. Like in this system, so it depends on your volume for these types of models. So here for this volume, 85 is great, right? That's like the natural maximum occupancy. We didn't see any trajectories when we sampled that went much above that. If I increase my volume, I'm gonna have to increase this, and then I don't know how I don't know how that's gonna scale. That would be an interesting thing to look at for sure. But you would need to then grow your cap.
Right. But the size of the tensors that you have to work with, right, are M by bond dimension. Right, so the size of all the tensors you have to operate on are growing with that M, so that can make that very bad, right? Where these things really would shine are where there's a small number of M, but a large number of sites, which is kind of the opposite of what we did, but now we know more.
Bro, I agree with most of that, but also it's not just the bond dimension, right? Because your bond dimension is going to grow as your system size grows. So if you satisfy this area law, then even if your physical dimension needs to be larger, if you get to set a fixed cap, like there is in the limit as the size goes to infinity, you can prove that there's some number that is going to be upper bounding your entanglement entropy is what they use for this. Then your bond dimension should be able to be capped, fixed. So then you still get more, there's still certainly more expense, but I think that would be the best case scenario where it's going to scale quite favorably.
Any other question? Yeah, yes.
One more. So the singular value decomposition, like, do you have some sense of what would make that the worst case? I feel like that's an interesting scenario. Like, where do you get a flat SVD?
Yeah, so I mean, mathematicians prove cases where like I have a 1D gapped Hamiltonian in a quantum system, then they can prove that you have this area law. But mathematically, you need to prove the class of systems to satisfy them. Here, we just hope that we had one. It turns out we did, because
Yeah, but maybe, I mean, that connects to the problem of what type of network to create.
exactly, yeah. So you have your dynamics of how correlation is passed around between your many body system as you evolve it in time. And then you have the structure of that network, how you encode that, and the two things together basically give you your tensor network.
I think our intuition suggests that if the network does not in some way resemble the if the tensor network does not in some way resemble the connectivity of the actual reactions, then that would put you into dangerous space.
Yeah, that makes sense.
But
I'm just wondering if you could like say, I want to impose that this be a flat SVD. What does that imply for how this network should be constructed in some simple problem? And then it won't solve the problem.
Yes, but it might give you insight into what.
Yeah, that's kind of the holy grail, right? Because then in practice, right now, what do? You pick a bond dimension and you run it and you get an answer. I grow my bond dimension, then I run it again. Did I get the same answer? If I got the same answer, then I don't need to increase my bond dimension. If I get a different answer, I do. If I knew ahead of time what was the singular values I needed to encode my dynamics, then life would be super easy. That would be wonderful.
Scott, can I ask a leading question? Because I basically, stay out of the technical weeds, but now I'll ask the question that makes you have to go into them. So it might seem like what you should naively do is just make the tensor network have the exact same structure as the chemical reaction network. Okay, like if these two things can talk to each other, let's connect them up with a tensor. Right, and so suppose you have a chemical reaction network with a whole bunch of loops. Like, what's the problem with me going and building a tensor network with that same loop structure?
I mean, the problem, why this is a leading question. The problem is that you lose some of the power of your tensor networks. So something I didn't all talk about, as it's not supposed to be a technical talk, is that if you give me a matrix product state, for example, I have an extra degree of freedom here. I have what's called a gauge freedom, which means I can take any one of these tensors and I can substitute it in where I put in a new matrix, X inverse and X from one side. And that doesn't, if I do that for all my tensors, I don't change my matrix product state at all. And so what it means is when I use this gauge freedom, I can put this thing in what's called canonical forms. So I can make it so it's left canonical. So that means that every tensor over here, we'll draw them with an arrow. Every tensor here is orthogonal with itself. And so this gives me a huge simplification in doing operations on my tensors. Likewise, I can do the opposite and put everything in right orthogonal. Or I can make just any one of these center site and everything else be left and right orthogonal. The reason I can do that is because I don't have loops in my tensor network. As soon as I put loops in my tensor network, I lose these canonical forms. And like the TDVP algorithm I talked about here, or you'll hear about DMRG, density matrix renormalization group, that like where I want to find my stationary state, these super efficient algorithms rely on having these canonical forms. So if I make my tensor network exactly match my reaction network, I may have the most efficient encoding, but I've thrown baby out with bathwater. I can't do these super efficient calculations anymore. Is that the
That seems correct, yeah, I mean,
is the answer you're looking for?
Thanks. So we're running out of time, so let's thank Sky once more.